Welcome to this video on LeetCode 1760, minimum limit of balls in a bag. We will transition from a brute force simulation to an efficient binary search approach to solve this problem. The challenge provides an array of bags with a specific number of balls and a limit on the maximum number of split operations allowed. Our goal is to minimize the penalty, which is the maximum number of balls in any bag after all operations. Initial instinct might suggest a priority queue simulation to always split the largest bag. However, with max operations up to 10 to the power of 9, simulation causes a time limit exceeded error. We require a mathematical approach. The key insight is to change the question. Instead of asking what is the best way to split, we ask, can we achieve a maximum bag size of X? This shifts the problem from optimization to verification. We can now use binary search on the answer X, the penalty. The search range is from 1 to the maximum number of balls. The problem is monotonic. If we can achieve size X, we can certainly achieve X plus 1, enabling binary search. To verify a target size, we need a formula for the required operations. To reduce a bag of size n to a maximum size of target, the operations needed is n-1 divided by target. Please go through the examples below. The -1 is critical, especially when n is perfectly divisible by target, because integer division in C++ rounds down. For example, 9 balls in a target of 3 requires 2 cuts, not 3. The algorithm starts with low as 1 and high as max balls. We binary search the mid-value, check feasibility by summing operations using the formula for all bags. If the total ops are less than or equal to max operations, we try a smaller answer. The complexity analysis shows that the binary search approach is highly efficient. Since the maximum value m is 10 to the power of 9, log m is approximately 30. This means the loop runs about 30 times, which is extremely fast compared to a heap simulation. This is the final optimized C++ solution, implementing the binary search on the answer using the operations formula for feasibility checks. First, we set our search range. We start low at 1, and high at the largest number in the array. Now, we run the binary search. We calculate the operations needed for our current mid-value. If that number is within the allowed limit, we know this answer is possible. So, we store it, and then try to find an even smaller answer by lowering the high pointer. Key takeaways are, to avoid simulation when operations are massive, look for binary search when minimizing the maximum, and leverage math, specifically the n-1 over k formula for instant split calculation.